All right, so we're taking a look at section 3.2. And what we're looking at is variation. So in section 3.1, we looked at what was called the center of data. This is sort of what different ways of trying to figure out where the data is gathering together. Is it sort of massing together in one location? It's sort of where you would call it the balance point of the data. And we looked at different techniques for trying to come up with this, or tried to discover what it could be. One approach is the mean, the other is the median, the other was the mode. And then we looked at some special versions of, well, kind of means is what we were looking at, calculating the mean for a frequency table or a histogram, and then looking at a weighted mean. So now we're going to talk about how spread out the data is. And what they do talk about in the beginning of the section, they mentioned this thing called quality improvement. So I'm just going to kind of star this. What they're talking about is, well, for example, manufacturing processes is the way I've heard it explained once was Arby's sandwiches. And the idea is that if you get an Arby's sandwich, say here in Roswell, and you go to Albuquerque, you would eat it, if you have a favorite sandwich in Roswell, roast beef and cheese, then suppose you go to Albuquerque, you would probably go to Arby's to try to get the same sandwich. Now, if it tastes different, if there's a variation in how these sandwiches taste from restaurant to restaurant, well, then maybe the sandwich in Albuquerque, the way they make it just doesn't taste as good for you as the one in Roswell. So you might not go to the Arby's in Albuquerque. Now, what Arby's does, though, and again, this is just an example, and I'm making this up, is, well, this part I think is fairly true. This part I think is fairly true, is that they do try to make the sandwiches taste the same in any city you go to. And the idea is that if you get an Arby's in Roswell, you know what the one in Albuquerque is going to taste like, and so you'll want to get one in Albuquerque. So they try to reduce variation in the taste of sandwiches. So this is the idea with quality, is we try to reduce variation in manufacturing. And you can imagine this again with like cars. Variation in cars could mean maybe parts don't fit as well in this car that just came off the assembly line versus another car. And that could be a problem. So you try to have the cars put together at the same kind of quality. So this is the idea of quality, and that's what they talk about at the beginning of this section. Now, the first kind of measure of spread, and we saw this before it was mentioned when we talked about mid-range as a measure of center. That was another measure of center, mid-range. And I just mentioned range, but what range is, it's the max value minus the minimum value. So max value minus minimum value. So for example, let's say again, this is your data. You want to find the range of this data. Well, the minimum value is going to be 1. The max value is going to be 10. So the range, 10 minus 1, or 9. So that's our range. Now, some points to make here. Observations. First off, it's not resistant to extreme values. It's not resistant to extreme values or outliers. So, for example, if we take our data here, I don't think I remember exactly what was here. Let's say we had something like this. Well, for this data set, again, the range is still going to be 10 minus 1. That's the smallest value, that's the largest value, and subtract the smallest from the largest, 10 minus 1, you're going to get 9. But if we change this one value to 1,000, now our range becomes something very different. Instead of 10 minus 1, we have 1,000 minus 1, or 999. While before, the range we got was just 9, because 10 was the largest value. So one value changes, everything gets thrown off as far as the range is concerned. So it's not resistant to these kinds of things, these large values. Another thing about it, it doesn't take other values into account. So one value changed, and the other 4 can't really do anything about it, and you still get this massive range. So it ignores these other values. Well, it doesn't ignore 1, but the 2, 4, and 6 are just out of luck. They can't influence what's going on at all. So it doesn't take other values into account. And then finally, these other values, a little more specifically, it doesn't reflect variation of other values. And again, I want to emphasize, well, I should emphasize, when I talk about other values, I mean values other than the minimum value and the maximum value. We do care about those when we talk about the range. We don't seem to care about anything else. So we ignore what's going on with all the other values. So that's what I mean by other values. Whatever is between the minimum and the max, we don't address that at all. So that's the range. So that's one way of looking for getting a sense of how spread out your data is. What's your largest value, what's your smallest value, and well, how much distance is between them. The other one we're going to look at is sample standard deviation. Now, what this measures is how much data values deviate from the mean. It's going to measure how much these deviate from the mean. Now, the formula could be a little complicated, where you symbolize it with the letter s, lowercase s. And we define it as the square root of the sum and remember, x bar is the mean. So this is your mean. Now, if you see this, this is the median. That represents the median, that's the mean. And we're going to have n, I equals 1 to n, lowercase n, have n minus 1. So this is the formula for standard deviation. So let me go through an example just to show how this works. I'll do a very simple example. And you might want to kind of keep this formula out. Maybe skip back in the video 10 seconds, jot down the formula, and then we'll put it together. We'll use it stepwise. So let's say we have our data. So to talk about indices, this is x1, this could be x2, and this is x3. So what we're going to do, we're going to calculate this thing. There's 3 pieces of data. We're going to calculate this. Now, what this means is for each data piece, we're going to subtract the mean from it, square that, and then add it to the next difference between the next data piece and the mean squared. Add that to the next data piece, subtracting the mean squared. I'll go through the steps. Well, we need a mean here, so we'll just review our mean formula. So remember the mean is x bar. We add up the data values, and then we divide by how many data values we have. And here we just so happen to have 1, 2, 3 data values. And sure enough, we get 2, which, that makes sense. That's the middle of our data. So that's our mean. That's x bar. So what we're going to do first, let's compute x1 minus x bar squared. Well, that's going to be 1 minus 2 squared, which is minus 1 squared, which is 1. Then we're going to calculate x2 minus x bar squared. Which would be 2 minus 2 squared, or 0 squared over 0. And then x3 well, that's what we're going to get for x3 minus x bar squared. So now what we need to do is we need to add each of these together. That's what that sigma sum means. This is for I is 1, I is 2, and I is 3. So we're going to add up each of these. So we get 1 plus 0 plus 1. That gives us 2. All right. So now if we take a look at our formula, we've figured out this part. So we figured out this right here. Let me get a pin here. See if this one works. No. Maybe this one. Yeah. We figured out this. It's equal to 2. So now we're going to take the square root of 2 divided by n minus 1. Now, n again is the number of data pieces. So we had 3. We get 3 minus 1. So we're taking the square root of 2 over 2. Over the square root of, or the square root of 1. And, well, that's just going to be 1. Because 1 times 1 is 1. So the standard deviation is 1. Now, if we think about what standard deviation means, it's a measure of how much the data values deviate from the mean. Well, the mean is 2, and well, this is 1 away, and that's 1 away, so it seems to be working. All right. Now, this is a pretty simple example, but that's how it works. So some things about standard deviation. It's greater than or equal to 0. With the exception, it's 0 when all data values are the same. And that kind of makes sense because if they're all the same, well, there's no deviation from anything. They're all exactly the same. So your Arby's burgers, your Arby's sandwiches are going to taste exactly the same no matter which town you go. So it'll be greater than or equal to 0, and it's 0 when all the data values are the same. Now, the larger of S means larger variation. So you're going to have a wider spread. And it increases dramatically with extreme values. Extreme values are outliers. All right. Now, there's one more thing about this, and we'll get to that later. It has to do with the issue of bias, but I'll save that for the next part when we start talking about population mean and population standard deviation. In other words, we've been talking about samples. We can find the mean for samples. We can find the standard deviation for samples. We're going to consider, maybe you call it hypothetical, but let's say we could find the population mean. We could find the population standard deviation. Is there a relationship between these and the means and standard deviations we get from samples? Anyway, I'll talk about that later, and I'll see you soon.